Afternoon, everybody. So what I'd like to do today is basically give you a 15-minute summary of what I've been up to with my team in the last roughly 24 months. And what I'd like to do is give you a bit of an overview of what roughly we'll be doing also within this QEO program. Now, some of you have seen recent talks of mine, and I like to keep tabs on scores. So today I'm going to be comparing classical methods versus quantum methods on this side over here. There have been a lot of talks, and there will be a lot of talks about quantum annealing, and there's, of course, a bunch of questions that we all want answers to. The first one is, of course, can a quantum annealer be faster than classical computers? This is also something that depends strongly on semantics. What is the definition of faster? But more importantly, a question that is very pressing is, can we find what we call synthetic benchmarks? In other words, designed problems where quantum annealers excel over classical methods. And I will show you several of the results that have been coming in over the last 16 to 24 months, as well as some of the things that we've been up to in the more recent months. And then finally, do customer applications exist where quantum annealing excels? It's one thing showing on a synthetic artificial problem that a quantum annealer is doing really well. It's a whole other thing to find a problem of interest, say, to a corporation or a government entity that actually shows massive promise over classical technologies. And in the application domain, the NASA team are really the ones that have been working a lot, so I encourage you to see their talks. Now, the work that I'll show today was done in collaboration mostly with Salvatore Mandra at NASA, but also with Alejandro Perdomo-Ortiz at NASA, Firas Hamzi at D-Wave, and Creighton Thomas at Google, as well as the guys that I work with at Texas A&M. Now, why does the Quantum Enhanced Optimization program of IARPA require test and evaluation? Well, for this, let me just in very broad strokes review once more the main goals of QEO. The goals are, first of all, assess the value of quantum annealing for applications of interest, such as constraint satisfaction, machine learning, etc., but also set the path for application-scale quantum annealers. And why do we need test evaluation? Well, the answer is very simple. The BAA has set the bar extremely high. And to put this in terms and numbers, it's requested there is a speed up over state-of-the-art classical algorithms of at least a factor of 10 to the 4. Not only that, but also an expectation for a scaling advantage. In other words, not just the offset, but also the slope. And there have been a lot of claims in the past. So the goal is really to take the elephant and throw it over the bar, hopefully finding the actual quantum speed up we're looking for. And what I'd like to do today is give you a case study, mostly based on D-Wave's quantum annealer. This is not the D-Wave quantum annealer. It's also a special purpose device. And show you some of the results that we have been doing in the last couple of years. Now, what is this thing? It's a special purpose analog annealer, emphasis on analog, so you have noise. It has about 2,000 superconducting flux qubits in its most recent incarnation. And as I said before, performance is controversial. And it depends very much on what do you call speed up, how do you find speed up, what problem you study, et cetera, et cetera. But the machine is a phenomenal technological feat. It can minimize problems in the cube format that can be embedded on its camera topology. And it does this using a sequential method known as quantum annealing. I think we all know basically what this is doing. The drawback, though, is that we have limited connectivity in its current version, which means that we are limited from a benchmarking point of view to very selected types of problems. And of course, you have analog noise, so you cannot really crank it up to very hard, very complex, very carefully tuned problems. You have to work within the parameters of this machine. And so a lot of teams have gone out trying to find problems that work really well. And I think one of the problems that really created a lot of buzz were the results mostly by Google, where there were claims of 100 million speed up over classical technologies. Now let me show you the results. What you see here is the time to solution in microseconds as a function of the problem size. And what I will do in this, as well as many other slides, is I will just add thick lines to highlight the results. mostly because very often you'll have data for different quantiles and many other lines and error bars, which make it a little bit difficult to see what is actually going on in these plots. Now, when you look at these data over here, these are made on very carefully crafted problems, the so-called weak-strong cluster problems, that are actually very, very neat. The idea is that you create these logical structures that I represent here by a gray box. So when you zoom in, you actually have two K44 cells where all the spins, really, Masood? Really? I already bored you? Jeez. Especially when I'm talking about Google results, you know? Sorry. So you have these K44 structures that are ferromagnetically coupled, and they are ferromagnetically coupled to each other. So you know that in the ground state, this should be just a giant ferromagnetic blob. However, one of them has a field pointing in one direction, and the other one has a slightly weaker field pointing in the other direction, meaning that if you use some kind of thermal anneal, it's very easy for the thermal annealer to land in a metastable state and get stuck. And now what you do is you take these weak-strong cluster problem, and you embed it in a spin glass backbone, and you generate a very hard optimization problem for classical annealers. So going back to the data, you see there's two important features when you look at these plots. One of them is the offset. You see that the D-Wave device is considerably faster in solving these problems than quantum Monte Carlo, in other words, simulated quantum annealing. And if you compare the difference for the largest system sizes, you see that there's about 8 orders of magnitude difference. This is one important ingredient, the offset. If the offset is, say, 10 to the 50, then even though the scaling might be the same, it's going to be a very, very long time before we can build a classical machine that can match this. But more importantly is the slope, the scaling. And you see that quantum approaches have a much flatter slope than the classical approach, in this case, simulated annealing, which was chosen as a comparison simply because these are both sequential approaches. So I would say that this is clearly a sign for a better scaling of quantum approaches, and if you go back to my scoring card, I would give it a 1-0 for quantum. Now what happens if you use other algorithms? When you say, let's just not restrict this to sequential methods, let's just pull out everything that we can come up with. And we decided, don't bother going through this, it's just a lot of words. It's going to be very clear in the next slide. And so we decided to pull out everything we can come up with. And in particular, there's 3 main classes of algorithms that we looked at. One are those that are tailored to the problem and or the underlying graph. In other words, we know what the solution is. We know that these gadgets are supposed to be ferromagnetic, so the logical structure of the problem is relatively simple to deduce. And you can do things like what we call the superspin approximation, where you just take each of these blobs and just replace it by one large logical variable. And so you reduce the number of variables, you can solve this much quicker. Another one is the Hamza-de Freitas-Selby algorithm that is also tailored for these tree-like structures, or the hybrid cluster method by Google that, again, is designed to work with knowledge of the actual problem. The other class are those that are not tailored to the problem. They are generic methods. One of them is population annealing Monte Carlo. The reason that we like to use that is because it's also a sequential method, but it's considerably more efficient than simulated annealing when studying hard constraint satisfaction problems. We also tossed our solvering, parallel tempering with isoenergetic cluster moves, and we did a variation I don't want to get into. And so we compared these tailored to non-tailored to sequential methods, keeping in mind the results using simulated annealing in quantum Monte Carlo. And we keep adding to this list. We have a few new things that we're testing right now that will come in the near future. Now, as I said, one thing that is important to me is the slope. And what you can do is you can take all these lines that you saw earlier, fit exponentials to it, and extract the leading scaling exponent. And this is what you will see here. On the vertical axis, you have the main leading exponent. Here you have the different algorithms. And there's 2 blocks here. There are red ones and the blue ones. The blue ones have a polynomial correction prefactor, so for simplicity, let's just focus on the red ones. But basically, the center line of such a square would be the leading exponent, and the size of the block would correspond to the uncertainty of the estimate. And this is now the whole collection of algorithms that we did on this. And now if you color everything in, you see a very specific picture. I remind you, smaller means better scaling, and I drew a line through Quantum Monte Carlo kind of as a break-even point. If this B is larger, it means the method is less efficient. If it's smaller, it means the method is more efficient. And what you can see right away is that within the sequential algorithm realm, Quantum Monte Carlo definitely does best. Even our state-of-the-art population annealing looks pretty pathetic in comparison. However, when you take now tailored and non-tailored problems, algorithms, the picture changes drastically. In particular, even the non-tailored algorithms can solve these problems much, much faster. So if we want to talk about some quantum speedup, I would say it's sequential at best. In other words, only within this class. So this means we get a tie. Now, earlier this year, D-Wave published an article when they released their D-Wave 2000Q, we keep calling it 2KQ, machine. And again, I will just remove error bars and all these things that make it hard to see the results. But basically, this is a time to solution in a logarithmic scale versus the number of variables in the problem. And you can see very nicely, again, Quantum Monte Carlo and D-Wave have very much comparable scaling, with D-Wave being a few orders of magnitude faster. And if you compare now to simulated annealing, you see again a better scaling. Now the problems that they studied, and I will get to these a little bit more detail later, are frustrated cluster loop problems. And there the ruggedness of these frustrated cluster loops is what fools thermal codes. However, the logical problem that is used to create these frustrated cluster loops is actually designed on the K44 cells as logical variables, meaning that you have a planar problem, meaning that it's relatively easy to decode the planar problem. And that's an issue simply because if you want to claim that your computer is so many times faster than classical algorithms, then you should look at all classical algorithms. And if the problem is planar, the method can be solved in polynomial time, and we have exact algorithms. So if you now were to use minimum weight perfect matching, and were to take this data and plot this in a log-log scale, the picture changes drastically. Here is the data that I showed you before by D-Wave, and here is now minimum weight perfect matching. And if you go roughly to this area over here, you are about 10 to the 40 times faster. So for this particular benchmark, minimum weight perfect matching solves the problems much faster. Now you might argue, fine, you're cheating because you know the logical problem, but it's relatively easy to write a wrapper that will render the method non-exact and that will tickle out this information. Good. So I would say it's a 2-1 for classical. Now very, very recently, the USC team actually looked again, and I think Daniel will be talking about this tomorrow, at problems defined on this camera topology. And there, again, the comparison was within the sequential realm. And we felt, well, what about population annealing? And again, population annealing is basically simulated annealing plus steroids. So it's a very fast method that usually is much, much more efficient than simulated annealing. Again, I'm going to show you the leading scaling exponent B. Here are the different methods. The blue blobs are the data by USC. Thank you, by the way, for sharing the instances. And here are our population annealing results. Again, smaller means faster. And you can see very nicely that even though population annealing is better than simulated annealing, it is far away from simulated quantum annealing. I should emphasize that for us to produce this result, we actually went ahead and we optimized the schedules for every single problem and made sure to use the exact same effort that was used for the simulated annealing runs. I do emphasize again, though, that one can use non-sequential algorithms, and these will again be faster than all the sequential ones showed here. So I would say it's, again, what I would call limited sequential speedup. Still, pretty impressive, I would say, is the first pretty solid evidence of limited speedup. So we decided, well, what can we do next? And I have to give full credit to Salvatore Mandra at NASA for the results that I will show you next. He came up with a very, very clever idea. Let's take frustrated cluster loop problems, and call them deceptive frustrated cluster loop problems. Basically, you start again with a C by C grid of logical variables. You can see a little cartoon here. The gray squares are the logical quantities, and you just have a spin glass backbone that is created by creating these frustrated cluster loops. The interactions of these logical variables, again, are bimodal plus minus 1. You embed this into the chimera lattice, but now, if I were to just single out these two folks down here, you see that within the K44 cell, these things are all ferromagnetic, and you have then the additional spin glass backbone. But now, unlike what was done before, Salvatore suggested, well, why don't we take the intercell couplers to follow the logical problem, but scale up these couplers by a factor S. And you see now what happens. If you take this bond right here, these bonds have all a value that is plus minus 1. And this guy here is going to be S times stronger. So if S is of the order of the number of neighbors that this spin here is feeling, then suddenly you get a very different ground state to the problem. What does this mean? If we start with S equals 1, then the ground state is given by the planar logical problem, which is what has been done so far, and you have death by minimum weight perfect matching. If now you choose S to be large enough, the ground state actually changes, you cannot retrieve it, and you will have no shortcuts. There is no algorithm that can solve this thing now in polynomial time. So let me very briefly show you the results. First, for S equals 1, and I couldn't resist because I called him FCL a la king, and it's kind of, jet lag, so I was thinking of chicken a la king, but that's a whole other story. Here you have the time to solution as a function of the lattice size. We're comparing just our solver, PT plus ICM, to Hamza de Freitas-Selvi, to the D-wave. And you see the D-wave is very fast, considerably faster than HFS, but our solver is still doing quite well. What happens now when we change this energy scale? Things change drastically. You see now that D-wave is still doing really well. It barely changed. Our solver completely crapped out. And HFS is still all the way up here. As a matter of fact, if I move this line down for comparison and back, you see that the D-wave is comparable, maybe a little bit slightly better, but this is still to be analyzed, than the best classical solvers that we currently have at hand. But the big difference, though, is that the D-wave is 10 to the 4 times faster. Salvatore will tell you a little bit more about this. And the last plot I want to show you now is, well, what do these slopes look like when you plot them for different scaling factors S? And this is what you see right here. This is very preliminary data. I ask you to please not interpret too much into this. But what you can see very nicely is that for small scaling factors, our solver here in light blue does really well. However, once the strength of this interaction is comparable to the neighbors, things change drastically. And you see that our solver has a lot of trouble. And in particular, when you go around here, which is roughly the sweet spot for S between 4 and 6, you see that the D-wave is performing quite well and very much comparable to HFS. Now, to say that we have a real scaling advantage is still premature. We need to analyze this in more detail. But I would say that this is a roadmap, this class of problems, for showing a potential of a scaling advantage, not just a constant offset. More importantly, I want to emphasize we have not a single algorithm in our toolbox at the moment that can beat the D-wave on this class of problems. And with this, I'd like to thank you for your attention. I would call it a tie because, I'm not inoptimistic. And, well, So again, I want to emphasize how important it is to design good benchmark problems. The killer application remains to be found. Stay tuned from QEO, and if you want a postdoc position, let me know. Thank you for your attention.
So for spin glass problems on a chimera graph, you studied these and you showed there was no finite temperature spin glass transition, and you said this was the most important factor with regards to them being good benchmarks or not. So do you understand anything about the phase diagrams of this class of problems, or even if there is a family of problems with nice properties as they scale?
So number one, I didn't say it's the most important thing. I said it's an important ingredient. Number two, this remains to be checked. You see, you could do a similar kind of study, except we don't have a, well, no, we kind of do. I shouldn't say too much. But it remains to be studied if the complexity of the actual problem, if it's P or NP, will affect the slope. Will it affect the offset? I'm not sure. I mean, you saw the offset is already pretty big. The question is, can it change the slope ever so slightly? And we don't know yet.
So one comment, one question. The comment you know.
Yeah, I know. That's why I'm shaking my head. No.
Right. So I'll let you say it.
No, we did not optimize the annealing schedules.
Oh, no. No, that's not it. Did you demonstrate an optimal annealing time? Because if you didn't, then you cannot trust the scaling.
Well, that's what I meant. I just use layman jet lag talk.
All right. And then I'll ask a question on behalf of Itai, because I suspect he might want to ask it, but there's no time. Have you considered something like a temperature-dependent HFS, where you, in other words, not the usual HFS, but where you allow for some kind of Monte Carlo updates?
We have not done that, but it's a good question. I'm not sure if it would work or how well it would work, but I guess Itai will tell us.
Okay, I think we're going to call it quits because it's late. But